Welcome, Professor Purusottam. His title is Complexity and Irrationality Measure.
Thank you, Srini. Happy birthday, sir. So, it's a pleasure to give a talk in this occasion. So, this is a project which started as a fun project in Paris when we were visiting last year with Patrice, and we found an interesting theorem in this context which was due to errors, and we thought of asking what could be a possible result of that in this context, which is complexity. We have definitely one, two, three theorems. There are 3/4 other things which we are trying to figure out. We are not sure whether we should try to prove it or to find a counterexample. So at least I will report at the very end things which we are reasonably sure that things are correct. But that will come at the end. Let me just explain to you why the type of questions which we are asking is so difficult, because it seems to mix two different invariants which are both in some way foundational to real numbers, but because they are so foundational, it is very difficult to prove a theorem there. It's more or less you are asking about figuring out real numbers from the very origin by base expansion or rational approximation. So let me just explain to you both the notions carefully, explain to you why they are so difficult, and there are one or two very few instances where they seem to affect each other. That also I will explain. At the very end I will talk what we have been able to prove in this context. Okay. So let me remind you what is an irrationality measure. So some of you might not have seen it. So typically the game is the following: you take any real number alpha, you take any epsilon bigger than 0, and you ask whether you can solve this. Of course you can solve this because rationals are dense. In fact you can get infinitely many p by q. So you sort of up the game by putting a parameter q now on the right hand side, which goes to 0 as q tends to infinity. Now in a spot of bother, because as you take q large, which you have to get infinitely many p by q, epsilon k tends to become small. So you are not sure whether this particular inequality will have infinitely many solutions or not. So the game is either you fix this function epsilon of q and try to find alpha for which this has infinitely many solutions, or reverse the game, fix a alpha and find the possible epsilon q's for which you have infinitely many solutions. And it is the second one gives me the definition of irrationality measure, where I choose epsilon q to be typically of the form q power minus theta. Okay. And once you work with this specific epsilon q's, you have, of course, if you have a solution for 1 by q power 500, you have a solution for 1 by q power 449, but you want to go above, so you take the supremum. So this would be a definition of irrationality measure of alpha. Supremum of theta for which alpha minus 1 by q is less than q power minus theta has infinitely many solutions in q. Okay, this is the definition of irrationality measure. Okay, and let me just tell you what we know straight away. Irrationality measure of alpha is equal to 1 implies alpha is rational. Okay, rational numbers of irrationality measure 1. If you take alpha to be irrational, irrationality measure is at most 2. Okay, for almost all alpha, irrationality of alpha is equal to 2. Okay, and the deepest theorem among all these three, if you take alpha in R intersection q bar minus q, irrationality of alpha is also 2. That is Rath's theorem. Okay, so algebraic irrationals have irrationality measure 2. So 4 theorems, all important. The deepest is this one. Okay, which one? Yes, bigger than equal to 3. Sure. So this is Dirichlet, this is Khinchin, this is Rath. Okay, this is something which you can figure out much easily. Okay, so this is, so already you see this should make you worried, because if you want to prove purely by methods like irrationality measure and want to prove some number is transcendental, that number most certainly will not belong to this set. it will belong to the set which has measure 0. So the generic numbers which are going to prove transcendence by Diophantine approximation are not going to the numbers which you really want to study in life, because almost every real number seems to be behaving like algebraic irrationals. So the numbers which you are going to prove most likely are which are sort of non-generic, like Liouville numbers. Okay, so it's worthwhile to make one more statement. Irrationality alpha is infinity. You can take it as a definition if you wish. Okay. So these are called the Liouville numbers. In other words, alpha minus p by q less than 1 by any power of q has one solution and infinitely many solutions. Okay, so this is one definition of Liouville numbers, and this is what more or less, and in fact this is one way of finding transcendental numbers which were found even before Cantor's diagonalized argument. We knew the existence of a transcendental number before we knew there are a lot of them. Okay, so this is what is known. So let me come to a recent result which will tell you how it is sort of tricky when you compare this with that. So you can ask the following question. Let me give you any number 2.3 pi plus 2, and you ask, can you give me a real number which has irrationality measure exactly equal to that? Is it true that every real number bigger than 2 is irrationality measure of some number? Well, the answer is yes. This even I think can be attributed to Jarnik. But something remarkable is true. This is a result of Bujo, which says I do not have to look at all real numbers. Give me any number 2.3. I am going to give you an element in the Cantor set itself which has irrationality measure equal to that number. So given any alpha, given let us say lambda bigger than or equal to 2, there exists alpha in the Cantor set such that let me call this maybe mu of alpha. Mu of alpha is lambda. So this is it was an open question of Malher for some time, and he proved this. In fact, he proved something much stronger. He said there are uncountably many in the Cantor set itself which has irrationality measure equal to lambda for any lambda bigger than or equal to 2. And why I am saying this, because if you remember the construction of Cantor set, if you write in base 3, one digit is always missing. So from a view of complexity, these would be what you called not the generic numbers, but with respect to measure. For instance, if you put 2 here, there are uncountably many elements in the Cantor set itself which have irrationality measure 2. Okay, but there one digit is completely missing from the picture. Okay, so let's keep this one. Will come back to even more refinement of this perspective. So in other words, Cantor set in itself contains all possible irrationality measures. Okay, so now let's come to the other side, the complexity story. Very good. So here you see, for all practical purposes, when you want to do irrationality or transcendence, it's enough to work with 0 1 open interval. You can always read mod integers that will come back to 0 1, and everything lies between 0 1. So take something in 0 1, fix a base is equal to 2 maybe, and you write alpha as, let us say, okay. So for every alpha you are associating this something like an infinite word with finite alphabet set being 1 to b or 0 to b minus 1. Okay. Now what is the complexity function? And if you take something bigger than 1, just look at the fractional part and take its base b expansion and call that the object which I am going to work on. So now for you simply look at this cardinality of the set. A1, A2, AN, A2, A3, AN plus 1, you look at all possible words of length L which shows up in the base B expansion. This is a finite number bounded at most by B power n. This is the complexity function of the real number alpha. Okay. Again, you have basic properties. P alpha n is strictly increasing unless P alpha is bounded, which is equivalent to periodic or eventually periodic, which is equivalent to alpha being rational. Okay. So, in this case just the way that one you have a big. So, here if you take a rational number, the complexity function will be bounded, or this would be eventually periodic, the sequence will be eventually periodic. So, in other words, if you omit this case, in this category you have the minimum number is n plus 1, because P alpha of 1 has to be 2 and is strictly increasing. So, P alpha of n is at least n plus 1. Okay. So, for alpha not rational. Okay. So, again you ask this set of theorems here. So, let me write here. Again you have a theorem which is similar to Jarnik's theorem, that this is Borel for almost all alpha. Something stronger is true, not only every word occurs with frequency 1 by b power n. Every word of almost, every word of length n occurs with frequency 1 by b power n. Okay. So, not only all of them occur, they occur with the same frequency. So, you will not be able to look, and so this you can think of analog of something like this almost all theorem. Now, what is the analog of this theorem? We have, so what is the best known? So, this for this one, right, you only have a conjecture. If remember, this says algebraic irrationals behave like the generic number, whichever is full measure. So, the full measure is b power n, so you expect the same thing. Okay. So, this is conjecture. Okay. So, in the both categories at least one thing is similar. I mean, this is perhaps similar in any Diophantine approximation theory, that if you have a Diophantine characterization and you have something which says, which is satisfied by almost all numbers, it is reasonable for you to make a conjecture that algebraic irrationals are in that set most likely. Okay. So, at least in one case you have an evidence, and this is conjecture. So, what is known? So, please remember, in this context you should treat this as what you called, if you were like that, this would be analog of a Liouville numbers in some way, and this will be the generic number. Okay. If you look at the if you compare the categories. Let me keep this one. So, please remember, irrationality measure is this statement. Okay. So, what is known about this one? So, we expect it to be p power n, then we know that it cannot be sublinear in n. So, the best known result, this is a wonderful work. That am I using p alpha of n? Yeah. Okay. So, the growth cannot be sublinear. Okay. So, when you look at this proof, maybe I should spend 5 minutes with this proof, because so typically when you, this is an analysis of maths, and people have been trying for this for 100 years, and you look at the proof and suddenly you are amazed at the very simplicity of the proof. So, maybe I can tell you what was the main new novel ingredient in this paper, and you will be astonished. So in principle, if you look at the proof, this is something which Smith could have proved. So let me tell you what is happening. So the game is, typically when you have a expansion like this, right? Please remember, if I truncate here as a p by q, what object here is 1 by 10 to the power n plus 1 or 1 by 10 to the power n, which is the same order of magnitude as the q which you are starting the game with. So you are not going to get something like q to the power 1 plus epsilon or 2 plus epsilon, you need a epsilon space. So best is you have a lot of zeros, which are leave the numbers. The next base is you have little bit of space. But even if you have little bit of space, so what happens if you truncate these numbers, right, and you just make it rational. So for instance, if you take this one and copy it as many times as you want, the typical numbers which show up, they look like this: a by some power of b and some power of b minus 1. This is how it will look like, okay. And you already see, so people were trying to use, it was clear to people that you are not going to use Rath's theorem because you have a b power n here. So the correct theorem would be to use Rideau's theorem, where you use the fact that one of the denominators is power of a fixed number, b power n. You can control a, because a would be typically less than this number. The whole problem was this object. You have no idea about the number b power m minus 1 as a random number. So the genius of, and they were all trying to use Rideau's theorem. So the genius of these two people is to use this wonderful observation that this number is actually equal to this number. B power n into b power m minus 1 is actually b to the power n plus m minus b power n. Then the genius is they were playing with one variable here. You have two variables here, but each of the variable, the loss is you have two variables, the gain is both the variables have a power of b. So if you have a theorem which is two variable or three variable, you are going to win, and that is subspace theorem. Just you have one more variable. So this astonishing that you use b power n into b power n minus 1 is as this, and now you have two parameters, and then for free you get the theorem. This is something any of us could have evolved, associativity, and then you would have got the theorem. So this is one of, in fact I would say this is the main point of the paper, just to realize that this is not the correct way of looking at the rational approximation, divided in two ways, and you just need three variables. So just one variable more than Rath's theorem, you don't even need even more complicated variables. Furthermore, the points which you are specializing are integers, you do not need any fancy language of heights or anything, just integers, you are going to win the theorem. So this is exactly the main point of the theorem of Pujo and Adamski. Just please make this, remove the bracket, okay. And of course, the second aspect is that suppose you have p alpha n of whatever this a n plus b is finite. So suppose they are bounded by 6n, okay, p alpha n. So you go from a1, a2, a6n plus 1, okay. You know total number of words of length n is 6n. I went from a1 to a6n plus 1, so there are at least 6n plus 1 words. So 2 must repeat of length n. So it could happen, you have here, you have here. So this is getting repeated here, okay, of length n. So you take the whole thing as u, take the whole thing as v, and you have a little bit space here. So you have a word which looks like u, v, and v power epsilon, and that epsilon space is all you need to use a subspace theorem. So this is the combinatorial game. Combinatorial game, you need an epsilon space here, and subspace theorem, just break the parenthesis. These are the two ingredients, and you have the theorem, okay. Very good. Now I am not trying to demean the theorem, I am just trying to say that the essential ideas are so simple and so elegant. Very good. So at least you do not have a theorem like Rath's theorem here, but you have at least this theorem. Very good. So, now you have two different contexts, you have complexity and you have Bjorn-Adamski, you have the theory of irrationality measure. Now, you start asking whether these two invariants are related to each other. So, let us start by asking the following question. So, if you notice here you have n plus 1 and b power n. So, this should be your what you call the special numbers, these should be the generic numbers. Okay. In that context, Liouville numbers were your special numbers. So, you ask what is the complexity of a Liouville number, you start asking. So, I think we started doing experiment, and to our surprise we found Liouville numbers with complexity b power n, which is maximal. We found Liouville numbers with complexity quadratic. So, then we started getting worried. So, the generic number which is b power n, Liouville numbers seem to have a spectrum of all sorts of complexities, and then we found this beautiful result, again Bjorn-Adamski. They classify all Liouville numbers which have this complexity. They say you take alpha, so that p alpha of n is n plus 1, then alpha is Liouville. Unfortunately, I have to use a term, the slope of alpha has unbounded partial quotient. By slope you mean you take all, you go up to n, count how many ones are there, divide by n and take the limit, it is an irrational number. So, a Liouville number will be a number with minimal complexity will become Liouville number if you look at the continued fraction of what is called its slope and if it has unbounded partial quotient. Wonderful result, again I think 2010 or something. So, you see matter is quite complicated. It is possible that Liouville numbers have complexity this, Liouville numbers have complexity this. So, you start getting worried about whether there is any relationship between this invariant and the invariant which is irrationality measure. This theorem troubled us. Then you have more trouble. Given any theta, there exists alpha, alpha is in Cantor set, complexity of is O of n and mu of alpha is theta. Inside the Cantor set, you give me any irrationality measure, I will find a number whose complexity is sublinear in n and the irrationality measure is theta. So, if you give me 2 for instance, which is almost every number, inside the Cantor set itself I will be able to find numbers which have sublinear complexity at the same time have irrationality measure which is generic 2. In fact, you can even ask, is it possible that I have a number which is an automatic number and still the complexity is theta? Well, you should not be asking for every number because the number of automatic numbers are rational. So, you cannot get every theta to be an irrationality measure of an automatic number, but if you insist theta is rational, then you can assume that alpha is automatic and mu of alpha is theta. So, you see it's a very weird conundrum where two invariants are there, the generic ones are becoming non-generic, non-generic are becoming generic. So, you have no clue whether there is any relationship between this invariant and that invariant, everything is getting sort of mixed. So, at least there is, so we are getting really troubled as to what is happening, but at least there is one theorem which seems to link these two, which is due to Adamski. So, take that's a mistake, C is ADAM SZE. C Z E W S K I. So take any alpha real and take the generic real number which has irrationality measure 2. Okay. Then P alpha of n minus n goes to infinity as n goes to infinity. This is a soothing theorem because this is one property which we expect for largest complexity, and you also expect for number which is mu of alpha is equal to 2. So it is a in some way a heartening theorem, and it also proves that P alpha of E minus n goes to infinity because mu of E is 2. This proof has no subspace theorem. It is purely combinatorial and little bit of continued fraction theory. But this is a good theorem because it brings you some faith that at least you have one theorem where both the generic ones seem to reconcile. Okay. So this is the trouble of the matter. So let me come to what we were interested in. All these things discussion started. We didn't know any of this theory. So which one? E. E. I think PE of n, that would be pen. You are right, this is terrible, PE of n. No, because the continued fraction expansion of n factorial is quite nice, so you can get the irrationality measure quite quickly. I think this is the first time somebody proved something about the complexity of E, that it is at least not n plus 5. It is not clear what to conjecture for E. You would say since everything behaves like b power n, E should be like b power n. But you see, it is not clear to which world E belongs, to Diophantine world or the special function world. I do not have a special function whose special value is equal to E. So I am not sure whether you should put E and pi on the same basket when you want to study transcendence. So it is, but you can be safe, put it b power n, because generally it is difficult to, if it is true, it is going to be impossible to prove in our lifetime. So you are safe, and if there is a counter example, fine. So
which is the expansion.
Yes, exactly. Okay, so let me come to what was our fun enterprise. How much time I have? 7 minutes, sir?
No, you have some 15 minutes.
Oh, fantastic. So let me tell you what we were interested in. So remember, with respect to irrationality measure, Liouville numbers, right, are what you called, which is equal to alpha such that irrationality measure of infinity. These what you call are the degenerate or non-generic numbers. So and it has measure 0 because we know everything else, irrationality measure of everything, almost every number is 2. So but it's a very wonderful theorem of Erdős is that okay, again the proof is so simple. L plus L is R. Every real number is a sum of two Liouville numbers. Okay, it is surprising because Liouville numbers are measure 0, but you know when you think about some set being small or large, it is more of about the structure of the set than the size of the set. For instance, I can take the real line, I can take a basis, I will just remove one point from the basis and look at the basis vector space generated by the complement. What I have removed is a line, I have the full measure, there is no way that sum is going to be R because there is one line which is going to be miss. So it is not just the measure of the size, measure of the set which would tell the sum set is large, whether there is a structure or there is no structure. If there is a structure, it will become small. If you add two if you add a subgroup with a subgroup, the order will be at most the order of the subgroup. So the fact that this is what we thought perhaps has nothing to do with the measure being small, but whether L has no structure. So we were asking what is the analog of such a theorem in the complexity world? What is the good set in complexity point of view so that A plus A is equal to R? And we had no clue, so we started by, and also one more thing is true. This is closed under action of Q plus L is also goes inside L, okay. If you add a Liouville number with a rational number, I still have a Liouville number, okay. So we started with sets which have complexity n plus 1, which would be the analog for Liouville, and both are false. Neither this is true nor this is true. Both the theorems are false. Okay. Then we went to sets which have at most polynomial complexity. Okay. So this is what I am saying is what ongoing work. Okay. So sets with polynomial complexity, at most polynomial complexity. Turns out this is false, this is true. Okay, so in first case both were false, in second case one true, other false. So then we went to the next one, which is okay, the one with maximal complexity. Okay, this turns out to be, second one is true, and finally we seem to have a theorem which resembles Erdo's theorem that m plus m is equal to r. So every real number is a sum of two numbers which have maximal complexity, and we thought it would be easy. So in fact I can tell you how did we prove. We started with the alpha, we found a beta which is nice, given beta we found a gamma which is nice, and beta and gamma were so nice that alpha plus beta gamma was nice, and alpha plus beta gamma minus beta plus gamma is equal to alpha. So in 3 level of construction we managed to prove that every real number is a sum of two Liouville numbers. Find beta, find gamma, so that this is normal, this is maximal complexity, this is maximal complexity, and the difference is alpha, and hence you get this. This is how we proved the theorem. So we were, this carryover is a pain. We have to be very careful. We have to do it in 3 level, and
Instead of polynomial, if you take exponential complexity but not b to the n.
no, we are not able to deal that. We know we are not able to deal that. B power n seems to work. N plus 1 doesn't work. Polynomial seems to work. Exponential we do not know. First thing, I do not know whether I have something which is exactly equal to 3 power n. It could be 3 power n plus 43. So you have to construct. It is not even clear to us that every nice function of R of n is actually, it will not be. For instance, you can have, it is not necessary that all spectrum of functions would be complexity functions. So you have to be careful what you want. So we could have a vacuous condition for all we know. B power n we know, n plus 1 we know. Everything else you have to construct. For instance, we know that numbers which have complexity n plus 1 are not automatic. That we know. Even though they have both linear complexity. So it is very surprising that you can find automatic numbers with absolutely whatever irrationality measure you want. That is really surprising. Okay. So this also was not easy for us. to prove, and we have to do some circus. But let me end by something else we managed to show. So we were troubled by the following set. What happens alpha p alpha of n is strictly b power n. Okay, so what you called the non-generic ones. Okay, so we know it is measure 0, so we want to know how big it is. So we want to study what is called as Hausdorff dimension. Okay. And
this candidate also you can't
polynomials, we can say highest, we can say, we cannot say that, maybe somebody else can say, but right now we cannot say anything. So what we could show at the Hausdorff dimension, so it is large from a Hausdorff dimension point of view, and for this we had to use a result of Pollington, which he again proved to prove another question of Erdős. So the complement set seems to be large, the set seems to be b power n, there are Liouville numbers which seem to be everywhere. So it is not at all clear to us that whether these two worlds actually coincide or whether there is any honest overlap, except that the result of Adamski which says if you have something which is 2, p alpha n is minus n to infinity. Other than that, rationals, okay, rationals are good in both the worlds. Other than that, it is not clear to us. Of course, we have not been, we are new to this topic, so whatever we have looked at it, it is not clear to us that whether these two worlds are there or there are some two Kafkaesque worlds into two different dimensions and not interacting with each other. But at least, so we have a couple of other questions in mind. As I said, sometimes we thought we have a proof, then we realize that there is something really troubling with the proof. So right now we have 2 or 3 questions which we do not know, as I said, whether to solve or to find a counterexample. So 3 days we try to solve, 3 days we try to find a counterexample, and luckily till now we have not succeeded in both. Okay, so I'll stop here. I think if you take a automatic number, the slope would be rational, right? If it exists. Slope means if you, no, the slope would be also rational. If you count, if you fix a b, how many b's are there and divide by n, I think it will be rational. Yes.
Suppose you take this set, the top set to be n, the alpha which is
This one.
so n plus m.
N plus m you will be able to figure out from n plus 1, but you will not have a theorem. In fact, that is one of the things Preeti is supposed to do, to figuring out n plus 1 and n plus b. It is not entirely clear. In fact, in many of the theorems, when you want to prove for n plus m, you make a trick to bring it to n plus 1 and then try to prove it. For instance, here, right? If you remember, limit of p alpha n minus n goes to infinity. This is not going to work if you n is equal to n plus 3, for instance. Okay. So it is not, as I said, we are new, but it is very clear to me if I put a scalar here, right, I am in a bit of trouble. Most likely we will be able to figure out the linear part reasonably well, but if I put a 2n plus 1, I don't know what to do with that. This one, q plus m? Q plus, so if you, most likely if you allow me all n plus k. So I suppose you are asking me if I take p alpha n is equal to n plus some.
No, he is asking L plus n.
L is what, Liouville numbers? And? This one. This one.
Numbers all alpha satisfying that property.
Sturmian sequences. Okay,
Summing in M.
which is
The maximal complex.
Yeah. The minimum
Complex
and
and
the
minimum
maximum.
and maximum complex.
okay. So I get your point. Take minimal plus maximal. So no, this should be inside this, isn't it? Because no, maybe not. No, let me not make any statement. So I have been wrong before, so I will not make any statements. So minimal plus maximal, I do not. No, I will be careful. No, I will be careful. I will be careful. Periodicity makes it bounded. You see. So once you put a factor of n, I will be careful. So no, but linear is still. I will be careful. So the fact that rationals are periodic, so it becomes eventually constant, is absolutely critical for our proof. So I am not saying it is not true. I am not saying it is true. Right now I do not know. So yeah.
What about taking two bases which are multiplicatively dependent, 2 and 3? If it is bounded into, not bounded, if it is little o 2 to the n and little o 3 to the n, is it rational?
I mean, my first guess would be yes. So to say, but again, I will be careful.
You will think that.
Yes, I think that. In principle, I mean, I get your point. Why are you asking this? But and I believe one should be able to. If one is smart enough, one should be able to answer this. But I believe it perhaps something which perhaps one can make some remark about it.
Minimal in two different bases.
Yes.
It looks very unlikely.
Yes. But I'll just be careful. I have been wrong before in this subject. So.
If there are no further questions, let us wish him all the best for, for his
Thank you.
So let's thank him once again for